Hello, everyone. So my name is Erica. So I'm from the commercial team at Tokamak Energy, and I'm in charge of intellectual property. And I'm here with Rob, who is the chief engineer of ST40. So we'll tell you a lot more about ST40 later, but that is our operating device at the moment. And we're here to talk to you about a bit about fusion in general, our company, and essentially pioneering commercial fusion energy. So can you all hear me okay? Yeah, fab. Fab. So let's start off with why fusion. So what are some of our current energy challenges? So I think we'll all agree that probably one of the biggest challenges facing us in our lifetime is climate change. And we're in a race against time to rapidly decarbonise our energy production. So we need to be rapidly developing alternative sources to traditional energy sources like oil, gas, coal. So energy providers actually need to be generating 22 billion less tonnes of commitments to meet the targets of limiting global warming to 1.5 degrees. There's going to be a bit of an ongoing theme about big numbers in this presentation, so watch out for that. So even beside climate change, another problem is that the non-renewable energy sources like oil, gas and coal are going to run out. So we need renewable or self-sustaining sources in order to be certain of our future energy security. And I think also in light of recent events, we're only becoming more aware of how important it is to have energy security and many different sources of energy. So linking into another problem, there's also only going to be an increasing demand for energy in the future. So it's estimated that by 2050, there's going to be 30% more consumers in the market, and there would need to be a 100% increase in electricity production to support decarbonisation and to enable the emergence of a hydrogen economy. So we want to give everyone in the world access to the same energy resources while securing energy security. But we want to do this in a way which doesn't damage our planet. And that's all adding up to quite a difficult task. So let's talk about what fusion is on a basic level. So can I see a show of hands of people who know what fusion is? Right, so keep your hands up, but I'm about to give you the opportunity to put your hand down if you don't want to be picked on for me to ask you what fusion is. So hands can now go down if you don't want. Okay, that's fine. Right, it's a small group. Come on, you can tell us what is fusion.
Okay, so every element plus hydrogen with one proton plus with two protons, two neutrons. If you combine them together, you get heavier elements, but that combination process can release quite a lot of energy. It takes lots of energy to do it, but the amount you get out quite far compensates for it. So they're showing you a diagram here. So once you're probably familiar with this fission energy, that's where you start from uranium and go to smaller and smaller elements. Peaking at iron. That's at the top of the diagram. That's the most stable element you can't get any more energy by breaking that apart or putting that together with something else. What we haven't achieved yet is sorry if I'm taking your talk.
No, you're doing a good job. Keep going.
What we haven't achieved reliably yet with some recent results is to go from the left to the right, going from the lower to the higher elements. So starting from hydrogen or helium, going up to lithium, beryllium, and even carbon. So if we can achieve that, there's quite a lot of benefits. First of all, we can see that the difference between the lowest on the graph to iron is much larger than uranium to iron. So the energy density is much larger. Also, hydrogen is freely available. You can get most of the elements from seawater, which is much more accessible than funding engineering and others that could get here. And yeah,
that's yeah, pretty good. So two minor comments. So I'm going to like scratch out most of what I had written on here. We have done it, but we'll go on to talk about that later. And you talked a lot about hydrogen. We tend to be looking more at heavy hydrogens. They tend to be the preference. So your deuterium and your tritium. But other than that, yeah, gold star for that. So yeah, I think that's most of that slide done. So well done. So why do we feel like fusion is such a critical part of the solution to some of these problems? So there are some really significant benefits to fusion power. So there's the zero CO2 power generation, which makes fusion an attractive prospect compared with traditional hydrocarbon-based fuels. Fusion is also a safe, controlled process with no long-lived radioactive waste, and that alleviates concerns associated with traditional nuclear power via fission. There's also a really high ratio of energy to volume of fuel. So 1 kilogram of fusion fuel provides as much energy as 10 million kilograms of coal. Fusion can also provide a consistent power source, especially when we compare that to some forms of renewable energy. So, we can't use solar when the sun isn't shining, can't use wind when the wind isn't blowing. And some renewable energies can also only be deployed in certain locations, which is not a drawback that exists with fusion. However, there is a bit of an elephant in the room before I keep on talking about how great fusion is that fusion is really, really difficult. So to see a considerable number of fusion reactions, you need to reach temperatures in excess of 10 million degrees. So for some context, the sun is 15 million degrees. And you probably want to remember this 10 million number because it's going to keep coming up again and again and again and again. So this raises a really big question for anyone kind of interested in fusion, which is how do you get something to these temperatures and how can you contain such a hot material? So I'm going to hand over to Rob now, and he's going to talk through a little bit more of the history of fusion research.
Thank you. So as a species, we've been looking at fusion research since about the 1940s, 1950s. And I'm going to take you a little bit through the history of how we've arrived where we're at and hand back to Erica. We'll talk a little bit about where we are today. So as Erica said, you need to get these particles really, really hot. So when you talk about nuclear physics, people talk about cross sections of reactions, and that's just how likely a reaction is to occur. If you look at the cross sections of fusion occurring, and as your friend rightly said, this releases a lot of energy. The cross section is incredibly small until you get to temperatures of around 100 million degrees, or about 10 keV in the language the physicists use. So how do you hold something that's, as Erica said, 5 to 10 times hotter than the centre of the sun? The vessels that we make are stainless steel, they're maybe tungsten, and these things melt at around 3000 Kelvin. So we tend to use magnetic fields. This talk's going to be focused on magnetic confinement fusion. There are other ways of doing it that we'll look at briefly. But as Tokamak Energy, we're looking at magnetic confinement. This is what you guys are going to hear about today. So if you have, as your matter gets hotter and hotter and hotter, you start with a solid. So if we take water, you've got ice, and then you melt it into water as you heat it up a bit, and then you vaporize it to make steam. And there's a fourth state of matter called plasma, which is even hotter than a gas, where you strip the electrons and the ions from the atom. What this means is because we can constrain them with a magnetic field. They don't like going across magnetic fields, so they tend to follow the field lines down. So if this is a gas or a plasma with no magnetic field, and the particles are just going in all the directions, hitting the wall, they're very hot, they're at sort of 100 million degrees, they hit our wall, they heat our wall up, our wall melts, particles get out. It's really not a good day for people like me. So we put these magnetic fields in and constrain the particles. And so in this sort of schematic here, we've got a really nice tube of constrained particles. However, we have two problem areas at the ends. And Edward Teller, who I don't know if you guys know, he was the father of the hydrogen bomb in the States. So he built the fusion bomb. And he said that confining a plasma with magnetic fields is like trying to contain a jelly with rubber bands. So as we go through and we design our devices, the plasma, you can imagine it like a balloon being squeezed, and it comes out between your fingers. So you put another magnetic field here to cover that bit, and then it squeezes out there. And we end up sort of trapping ourselves with building more and more elaborate magnetic traps. And so this is a bit of a history of how we've kind of done that. So the first thing you can do, and I guess you guys at the front study physics, right? So I'm going to butcher this, and you can keep me honest. If you can build a magnetic mirror. So if you increase the field locally, you get a mirror effect, much like a mirror acts for light. These magnetic mirrors act for particles. So you've got, as we said, we've got our tube that we've made with a magnetic field. Things are trying to come out the end. We've made a mirror here and a mirror here, and we're kind of home, right? Because we've trapped the particles in the tube, we've blocked the ends. Unfortunately, it's not quite that easy. It's not a perfect mirror, and it depends on the exact velocity of the particle, the direction of the velocity of the particle, how effective that mirror is. And you will always end up with some that are in the wrong position to be trapped by the mirror and will end out. So if I take the next slide, the mirror machines got bigger and bigger and bigger as we built them, and they culminated really with something called MFTFB, which was built in 1986. I'm guessing not many of you guys were born in 1986, right? It might just be me. So this was built at a place called Lawrence Livermore, which is one of the big national labs in the States on the West Coast. And this is the schematic of what the machine looks like. So we've got our famous tube in the middle with all the particles constrained. We've got the choke magnets, which is where the magnetic field goes up by about a factor of 10. And that's about what we can do. Stronger magnets mean today's technology, we can maybe get a factor of 20, factor of 30, get that loss cone down. It's not going to be enough because we're always fighting a bit of a losing battle with this. And then they've got what the Americans call the yin-yang coils, or the British call the baseball coils at the end, which were designed to produce this weird field shape and really augment the mirror design. But it still doesn't work particularly well. So this is a schematic of what it looked like. It was abandoned in construction. This is a van for scale to give you an idea of the size of the thing. I'd point out it's an American van as well, so it's largely what we think of as a van typically, and you end up with quite a big thing. When we talk about particle traps, we're going to talk about confinement times, which is just a measure of how successful you are at trapping the particles. The longer the confinement time, the longer I've kept the particles and the energy together, the hotter I can get it, the more chance of a reaction going. The confinement time on this is about 1,000 times weaker than a contemporary tokamak. And so that's why we've arrived at tokamaks. And I'll keep going to see how we got there. Thanks. So, someone much brighter than me once said, well, we've got a problem with the ends of the tube. Why don't we fold it into a donut and then we've got no ends? And this is a really neat solution. So this is what we would call a torus, or a donut shape. And this was going on in the 1950s. So we built bigger and bigger toruses. And on the next slide, I'll talk a little bit about what the problem with toruses are as a particle trap. But they got bigger and bigger, and they tend to be unstable. So because physicists have very active imaginations, they come up with very descriptive names.
Boy, be careful what you say.
So you've got the kink instability, which is this one here. And this is where the plasma grows in a bulge. As it grows in the bulge, the constraining forces get weaker, and so you have this positive feedback, and suddenly you can't stop the bulges forming, and the plasma looks like that in microseconds before it collapses. You have the sausage instability, which is where the plasma separates into what looks like linked sausages that you would buy from the butcher around. And we have everyone's favourite magnetohydrodynamics, which I'm not really qualified to talk to you about, so we're going to just gloss over and move on. So eventually we built bigger and bigger these machines, and a good example is built at Harwell. So in Oxfordshire, there's like a rich history. There's Cullen Labs, which is about 10 miles south of here. There's Harwell, which is across the road from them. And these things were really pioneering places through the early history. And so Zeta is this machine here. It's supposed to be a zero energy pile. And interestingly, it had good results when the field reversed. So it's a bit complicated to explain. Maybe if I take the next slide, we'll come back to that. So the problem with pure toruses. we want to run our particles in a circle. So we need a magnetic field going in a circle. And this is quite easy to arrange. We put a big electric current through a wire and we generate a magnetic field. So far, so good, right? The problem is the field drops off something like 1/r. And what this means is things tend to drift outwards from a pure toroidal position. There are reasons why this is to do with the field gradients and the electric field gradients. But the simple way to think about it is, and I'm sure as many people, none of you ever do this, but if you drive too fast round a roundabout, the car tends to drift outwards, and particles want to do the same kind of thing. So the plasma physicists will talk about particle drifts, and a lot of the game is about stopping the drift, stop the particles drifting outwards, because as they drift outwards, they're lost to the plasma, their energy is lost to the plasma, and the game is about keeping enough energy in that they can react and release more energy than we put into them. So there are two ways out of this problem, or the two ways we've so far worked out that will take you out of this problem. The first one I'm going to talk about is something called a stellarator, and this was a guy called Lyman Spitzer in the States in the 1950s came up with this. And he was working out of Princeton at the time, and he said if you arrange a magnetic field, so instead of going in a pure torus, it twists as it goes round. So in this image here, you see the pink being the plasma, and it's twisted as it goes round, a bit like a Mobius strip. And so the plasma spends half its time on the inside, where it's quite good, and it's drifting into the core of the plasma, which is a nice thing to do, and half its time on the outside, where it's drifting away and the energy's being lost, and that's the things we don't really want to do. So personally, I quite like stellarators. Officially, I'm not supposed to say that, but they do quite a few.
What's your mouth about?
They do quite a few nice things. So we'll talk about the tokamak later and how we get around this problem in tokamaks. And it's to do with something called the plasma current. Because this field's built by static magnets, it's easier to control. So we can keep it sort of controlled. What's worth saying is stellarators and tokamaks, when you plot them on a graph on one-dimensional parameters, they have about similar performance. So it's not clear that one's significantly better than the other. It's a bit of a case of choose your poison, which most engineering seems to be. So the last couple of slides on our walk down sort of memory lane, we've got the tokamak. So in the 1950s, in the Soviet Union, these physicists came up with an idea called the tokamak, and it's an acronym for toroidal magnetic chamber. It was very, very impressive results at the time. At the time, the technology we had to build magnetic fields meant we couldn't build a stellarator with anywhere near this performance, and they were the first people to achieve the magic sort of 100 million degrees Kelvin, or about 9 keV. So they came over, and actually at Cullen down the road, they gave a presentation where they discussed their results, and no one could believe how well it had gone. And they sent a team from Cullen to Russia, and this was in the early 1960s, when these kind of travel was really not well known, and they verified the results. So let's have a little bit of a look at how a tokamak works. So we talked about the magnetic field going round. So we've got a current going up the middle. We've got a magnetic field from that, which we call the toroidal field, going round, keeping our particles. We want to arrange it so our particles spend quite a bit of time on the inside and a little bit of time on the outside. So what we do is we put the plasma current in. So the plasma current is shown by that green arrow there. How you put the plasma current in is a very difficult question that we'll pause for now. So the plasma current's going round, and it generates what we call colloidal magnetic fields. So that's the one that's shown by the green arrows there. And what that means, when you superimpose these two magnetic fields together, you get a shape that looks a bit like if I take the barber's pole and bend it into a torus. So if you want to visualize the particles going around, imagine that pole bent round and the particles kind of do that. And we've got a fancy little animation that was done by someone much better at PowerPoint than me. It shows you here. So particles going round this way, at the same time it's going round this way. This is projected onto a single plane, which is what we often do for simplicity. But you can see this very sort of complicated pattern that's made. So I said the big question we really have with tokamaks, because they've proved very reliable as confinement traps, we've got good empirical knowledge of how they perform, is how you drive the plasma current. So this plasma current is very important for stability. At the moment we use a solenoid and generate a loop voltage. We can't going forwards for longer term devices, and I'll come back to this later in the talk, this is something we need to develop different ways to do it. And part of the talk will look at how we would do that. And so that's kind of a look at the bit of the history. I'm going to give you back to Erica, who will take you through kind of where we are today.
Thank you. So yes, I'm going to talk us through now. We've kind of done the history. Let's think about some of the kind of really key results that we've had in our quest to get to commercial fusion. So before I talk too much about the results, I think it's really important to talk about one of the parameters that's about to come up a lot, and that's the fusion energy gain factor, which we refer to as Q. So Q is the ratio of fusion power produced in a nuclear fusion device to the power required to maintain the plasma in a steady state. So essentially what you need to remember is Q greater than 1 is a net energy gain. It's also really important to appreciate that it's been a significant scientific and engineering challenge to get any Q which is a significant positive number, let alone get Q greater than 1. So I'll start off by talking about the Joint European Torus, or JET for short, on the road in Carlins. That's about 10 miles from here. As the name suggests, this project was a joint effort in terms of funding and resources from a number of different European countries. JET is what we refer to as a conventional tokamak, which means it's shaped like a donut. And it has a major radius, which is the distance from the centre of the donut to the outer edge of the donut of 3 meters. So the first key result from JET was when JET achieved Q of 0.67, so not Q is greater than 1. And that was back in, do you remember the year?
97.
Oh, it's on the slide. Yeah, 1997, there we go. And the second key result was in 2021, which was when JET produced 29 megajoules of power over 5 seconds. Now, we've been thinking today about how we explain what 29 megajoules of power is, and it sounds varyingly impressive depending on what you compare it against. So the one that I think sounds most impressive is that's the same as 200 hand grenades. The least impressive one, in my opinion, is it's 60 kettles worth of water, which doesn't sound great. But what was significant about that was the over 5 seconds part. So whilst that seems like a short amount of time, that was essentially the maximum time that JET was ever designed to sustain plasma for, and it meant that that amount of you were getting a kind of steady amount of energy out of the tokamak, rather than the result back in 1997, which was just a really sharp peak. And it's that kind of longer, kind of even distribution of power. That's what we want in terms of a power source for the future, rather than just massive spikes that come randomly. So that is why that is an important result, even though it sounds a little bit insignificant when you think about the amount of energy. So there's also been some major developments in the US. The UK can't take all of the credit for developments in fusion. So another really important result occurred in the later half of 2022 at the National Ignition Facility in the United States. We call them NIF for short. There's also a lot of acronyms. I should have pointed that out earlier. So NIF is investigating different ways of igniting fusion to magnetic confinement, which Rob talked us through earlier. So this different process is called inertial confinement, which I'll explain briefly. So in this method, there's a target which is filled with fuel, which is compressed and heated. So the targets are typically small pellets containing 2 forms of heavy hydrogen. So energy is transferred to the target's outer layer, produces shock waves that travel through the target, compressing and heating the target. If the shock waves are powerful enough, they can generate fusion. And given the very large amount of energy transfer that you need in a very small area, it's lasers that we use for this. So, for example, at NIF, there is a laser system which guides, amplifies, reflects, and focuses 192 powerful laser beams onto a target, which is about the size of a pencil. So on to what the result actually was after that brief detour. So in August 2022, NIF demonstrated a net energy gain, so that was Q greater than 1. So that was a really significant result in the fusion community, and it got a lot of press. So to give you an idea and put some more perspective on it, the peak pressure that was obtained during the shock that achieved this result was 500 billion atmospheres, so a lot. One thing to kind of point out when we're talking about Q and Q greater than 1 and what it means is that although it's a hugely significant result that demonstrates net energy gain, it is also estimated that in order to make fusion an effective power source for the grid, we need devices that can operate at Q greater than 20, 25. So there is a massive way to go in terms of how much energy is being produced in these reactions. So now to talk about our own world-class result at Tokamak Energy. So as I mentioned briefly earlier, our current operating device is ST40. So ST40 is a spherical tokamak with copper magnets, and it has a plasma radius of 0.54 meters and a toroidal magnetic field of 2.1 Tesla. So just also there to point out how much smaller ST40 is than JET. It's tiny in comparison. So and also to talk a little bit more about what a spherical tokamak is essentially we talk about that as being a donut compressed to its limit. So it kind of looks like a cored apple, which is demonstrated quite nicely in the figure on the right-hand side. So just over a year ago, ST40 achieved an ion temperature of 100 million degrees. So such a high temperature has never been achieved in a spherical tokamak before, only on much larger devices. So this really was a kind of proof point for us that spherical tokamaks as a smaller device could get to these fusion relevant temperatures. And also exciting, if you want to read in any more detail about this, is that we've just had our peer-reviewed paper published in the Nuclear Fusion Journal. So if you want any more information on exactly what we did, how we got the result, all of the information is there, explained far better than I could ever do. So I'm now going to pass on to Rob, now that we're really well and truly into spherical tokamak domain, and he's going to talk some more about this technology and our high temperature superconducting technology.
Cool. I'm going to talk to you a little bit, as Erica said, about spherical tokamaks and high temperature superconductors. These are the two key technologies that we at Tokamak Energy think make this sort of energy source more viable. And the HTS is really a key enabling technology for the spherical tokamak, and so it feels like an idea that's time has come because of the progress in the HTS. So why spherical tokamaks? So as Erica said, if you see the top image of the pink there, the conventional tokamak, the plasma has a shape a bit like a car tyre, so it kind of goes round in that donut shape that we talked a lot about in the earlier part of the talk. The spherical tokamak compresses everything onto the major radius, so everything gets closer to that axis where the toroidal field current is going up to drive that magnetic field. So why do you want to do this? Well, near the central column, the toroidal field is stronger. We said that the field drops off 1 over r, and so in the area of stronger magnetic field, you've got better tracking of the particles, better confinement. So you keep everything here, the smaller pink shape, there is more proportionally close to the center than far from it, relative to the other one. Good curvature is another physics term that has, very good connotations. You can imagine what they're trying to say. So this is the area that the physicists would call good curvature, and this is the area of bad curvature. Now, why is that? Particles, as we said, are trying to drift outwards. So if you have particles here, they're going into the main core of the plasma. The energy is trapped, and things can get hotter to a temperature where fusion can occur. Particles here, they're drifting outwards. You lose a particle to the system, you lose the energy containing that particle, and it counts on the negative side of the balance sheet, right? And we're trying to get that balance sheet as high as possible. As Erica said, we're aiming for a Q of sort of 20, 30, something like that. So this is the shape of the magnetic field lines. So this is how they circulate in a conventional tokamak. You can see the particle spends approximately half its time on the good curvature side and half its time on the outside, the bad curvature side. On this one, you can see the particle spends a lot more time on the goods curvature side because the field is relatively stronger here to here, so it spends a lot of time going around and then is recycled quite quickly back to spend yet more time in the centre. So this is really, really a good thing. To come back to one of the more complicated aspects of tokamaks and the plasma current. So we talked about needing a plasma current to get the confinement, to get that colloidal field. We talked about needing to drive the plasma current. And this is a difficult thing to do. There are various ways you can do it, but they're all really quite energy intensive. And again, we're talking about an economic thing here. So on the balance sheet, we have to generate a lot of energy for not putting a lot of energy in to make the electricity cheap to produce, to make it dependable, to mean you can black start a power station, which means if the grids are out, it's very difficult to start them because you haven't got the power to get going. And so we used to look at this a lot with coal power stations. So how do you drive plasma current? We use RF heating, so we can put radio waves in, and if we get the phasing right, you can tend to drive particles in a direction, and this drives a current. You can use neutral beams. You can fire a big beam of particles, and obviously they've got a momentum, and that just gives you a plasma current. As I said, all of these are very energy intensive. So the nice thing about the spherical tokamak, and it's a bit complicated to go into here, is it self-drives a lot of the plasma currents. The results from MSTX at Princeton in the States have shown that a spherical tokamak can self-drive 95% of the current you need. So that's 95% we don't have to drive. We don't have to use energy off the grid to drive that. And it helps the economics massively. And the reason, for those that are interested, is because you have higher gradients of field and pressure. So, why isn't everyone building spherical tokamaks? Because I'm selling a good picture here. The difficulties are around the engineering. So everything's compressed in. It's a much more energy dense system. The fluxes on that centre tube are immense compared to the centre tube here. And by fluxes, I mean neutron flux. So neutron is a subatomic particle. It damages the material as it goes through it. The material ages. And it's one of the problems we're going to have to sort out. And it's exacerbated in the spherical tokamak. And the same for a heat flux. And we'll come back to talk about heat fluxes in a future slide. So if we go for high temperature superconductors, so I guess all of you are aware of superconductors? Yeah. So as Erica said, the jet pulses are limited to 5 to 10 seconds. And the reason for that is a trick we like to play in the research community called inertial cooling, or doing nothing. So you have your magnet, you run your current through it, it's heating up because of the Joule effect. You just stop before it gets too hot to damage itself, and then you wait. So jet can do about a 10-second pulse every half hour or so. ST40 can do a quarter of a second pulse every 20 minutes or so, because we just stop before things get too hot. And this is a really cheap way to build research machines. The results in the short term are valid as long as you get past about a quarter of a second. And the reason for that is things happen in very, very fast timescales on the order of microseconds. So if we do an experiment about a cup of tea cooling down, so I come here, I put my cup of tea down, I'm quite a forgetful engineer, so I leave it be. If you come back after a quarter of an hour, it's a little bit colder. If you come back half hour later, it's colder. If you come back an hour later, it's roughly at room temperature. If you come back at 10 hours later, it hasn't changed from the hour. So we talk about characteristic times. And so 1 hour is about the characteristic time to get into steady state for this cup of tea that you've left on the shelf. In a plasma, because things happen on the microseconds sort of time scale, as you get to about 100 milliseconds, you can call it steady state for plasma processes. And what this means is your tokamaks, your plasma research machines only have to run for fractions of a second or a second to give you meaningful results. And it's a cheaper way to build tokamaks, which means more money for me and my donors, which is good. So we've played that trick on the research machines, but it won't be very good for a power station, because if I told you guys that you can only turn the kettle on for 5 seconds every 20 minutes, I don't think you'd have many customers. So we need to find another way to do it. And the obvious answer is superconducting magnets. So superconducting magnet is nice. It has zero resistance by definition, so it takes zero power to run the magnet, which again helps in that sort of economic balance sheet of how we build up the energy we expend versus the energy we gain, and what's left obviously we can sell. So What's very well known about superconducting materials is that they have a critical temperature. So there's a temperature below which they are superconductive, and a temperature above where they're not. They're normal, there's a resistance, things and current through them. What's less well known is it's actually a surface. The critical temperature that's reported is the zero field current. And there's a surface inside which is superconducting material, and outside it's not. And this surface is a function of temperature, magnetic field, and current density. Now I'm building a magnet, so I need it to work in a magnetic field. So magnetic field is not zero. So already we're somewhere in this surface. I want the magnet, I've spent time and effort building it, putting it where I want. So I need a current density because that's how I build magnetic field. And so I'm not here. And so you're somewhere in this surface, and making this surface bigger makes the plant more economic. We can operate at higher temperature. And for those of you that know a bit about thermodynamics, obviously the colder I need to pump heat away, the more of an energy penalty that the Carnot cycle efficiency kicks me for to make that happen. So the high temperature superconductors give you a big efficiency saving by reducing load on the cryogenic system, but they also at the same time allow you to have a higher magnetic field. And this is a key point. So we talked about spherical tokamak, we've talked about compressing everything onto our axis where the fields are high. And our initial results indicate that higher magnetic field really increases particle confinement. So why is that? Well, I told you a bit of a white lie earlier. When I said that particles go along field lines, it's not quite true. They spiral around them. And so the higher the field, the smaller the spiral that the particle will go around on, because the force that's binding it to that line is smaller. So we've got particles going along adjacent field lines. Obviously, the bigger they're spiraling around, the more chance of collision between them. And collisions between particles is a bad thing for us. It creates turbulence, it creates sort of movement in the plasma, it creates loss of confinement of particles because now you've put an external force on it and we've lost control. It's not in our nicely designed magnetic trap. So the higher field gives us less collisions, better confinement, and is possible with superconductors. And that's why the two technologies really kind of marry together quite nicely. I'm going to hand you back to Erica.
Fantastic. So we're now going to talk about kind of some of the strengths, a bit more specifically to our company, Tokamak Energy. So obviously, as kind of Rob's already reflected on, we really see ourselves as pioneers of the spherical tokamak and of HTS, and kind of how well those two pieces of technology go together. So we're also really proud of our track record of building and operating devices. So just to take you through a little bit of our history. So in 2013, we built our first working prototype to validate the spherical tokamak approach. In 2015, we went on to combine high temperature superconducting magnets with a spherical tokamak, and by doing that, we achieved a plasma pulse of greater than 29 hours, so a lot bigger around in terms of time. So then in 2017, we constructed ST40, which is our high field spherical tokamak. And 2 years later, in 2019, we recorded a plasma ion temperature in excess of 15 million degrees. So that's the temperature of the sun. So 2019 was probably quite a busy year for us because we also achieved a world first HTS magnet achieving greater than 20 Tesla at 20K. And the same magnet was tested a year later in 2020 at CERN, and that achieved 26.2 Tesla at 4K. So then moving on to last year, 2022, as I've already mentioned, we had our world first of achieving 100 million degrees in a compact spherical tokamak. So what's next on our timeline? So our next device will be ST80 HTS, and that's going to combine our HTS technology with a spherical tokamak on a large scale. And that's going to be built down the road in Culham by 2026 is the aim. So exciting, happening soon. So one of the things that we're also very proud of about our approach is kind of how we tackle challenges and break them down. So we've kind of appreciated that spherical tokamaks and HTS provide us with some of the solutions to commercial fusion, but they are by no means the only challenges that we're facing. So we've broken down these challenges into 12 key building blocks, which are key technology and science development areas. And we've been working over the last year to break down exactly how we meet the requirements in our aggressive timescales. So Rob, in a little bit, is going to go on to talk about 2 of these building blocks in a little bit more detail, the challenges we face and how we're thinking about overcoming them. But for now, the main take, we've got a plan. So our kind of third key point about us as a business is that we're really focused on a commercially deployable solution to bring to market in the 2030s. So this is an ambitious goal, but in order for fusion to play an important role in sustaining a zero CO2 future, we need to focus in on making fusion a reality as soon as possible. And we really do strongly believe that our combination of a compact spherical tokamak with high temperature superconducting magnets, as in combination with our plan for developing the key other enabling technologies, will mean that we can offer a compact, efficient and low cost solution. And that we believe that that means that our solution will also be globally deployable. And that will help to address the increase in global energy demand in the future, as well as helping to secure energy for all. So I'm now going to hand back over to Rob again, who's going to talk through some of the challenges we're facing in some other areas in a little bit more detail.
So decided to talk about 2 real key challenges. They're by no means the only challenges. As Erica said, we've got a program of 12 building blocks and how these are broken down. But 2 are quite interesting, and so we'll give a bit of discussion really. So one is the high heat fluxes. So we've got these really high energy particles. As we said, we're changing hydrogen isotopes into helium. What this means is we generate helium in the plasma, and somehow we've got to get rid of it. And so we get rid of it onto something called a diverter. And what that means is we're driving particles down onto the diverter surface, which I haven't got a good picture of, but is up in that top picture there. Doing this leads to large heat fluxes, and as I said earlier, the spherical tokamak exacerbates this. Everything's compressed on the axis, the areas are smaller, so relative fluxes are higher, and it's hard to deliver the same amount of power. So I put on a chart here, and notice the sort of log scale, some of the things that we might be sort of familiar with that we think are high heat flux. So your domestic radiator at home, it's about the limit of what you would want to touch with your bare hand without burning yourself. You know, it's here down at about 1 kilowatt per meter squared. So we get a little bit more exciting. We can go to coal furnaces in power stations. Sadly, I used to work in power stations and find them quite exciting. So, but you can see this here. This looks like a real roaring fire rate. It looks really, really quite aggressive, and it's not yet 1 megawatt per meter squared. The welding torch. The welding torch is again a pretty aggressive thing. I can hold it on a bit of metal and melt that metal quite quickly. Is somewhere around a few megawatts per meter squared, so probably around 5 or 6 megawatts per meter squared. Then the diverter infusion, we think this machine will need to accommodate somewhere around 20 megawatts per square meter. So this is a huge number. It's about 1 million times more sort of heat per unit area than your domestic radiator, and about a factor 10 more than a welding torch. So designing the materials to be able to survive that level of heat is really challenging. The only thing I can think of that's more aggressive in terms of design is a rocket engine, and they take somewhere about 150, maybe 200 megawatts per meter squared, which is phenomenal. But the thing to remember is a rocket engine is in orbit in about 90 seconds, so it's only got to survive 90 seconds. Now, to be fair to SpaceX, they do have some reusable ones now, but still the integrated time of, say, 100 launches in 90 seconds is measured in minutes and maybe an hour. Whereas this diverter in your power station, you want us to be able to turn it on and leave it for 20 years in this nasty environment without it sort of self-harming to an extent where we can't repair it. So what tricks do we have to get away with this? Well, as you all know, things get hot, they expand. So we design what we call kinematic mounting. And so the thing's going to get hot, we need to allow it to expand. And we have all these tiles that sort of expand around each other, cover each other, and the design of the mounting's key. The other point that's really important is because the heat comes down on this surface and is drawn out the back, you end up with a temperature gradient. So that expansion isn't linear. It's not a plate that's expanding in all directions. It's expanding more on its top surface and the bottom. As you get what we call hogging, this kind of shape that goes up into a dome shape, which I've tried to show here in the schematic, but it hasn't come out very well. So sorry for that. But imagine this plate is making this kind of shape in 2 dimensions. So we design our mounts so that things can rotate and they can slide one way and accommodate all this differential movement. These get cycled, so the stresses get cycled on and the material fatigues. And this is one of the really big challenges to solve. The other one that I'll bring to your guys' attention is plasma control and diagnostics. So at Tokamak Energy, we're quite proud of how we control plasmas. You know, we've got our Tokamak ST40. We drive on a good day, maybe 30 to 40 plasmas, which we control, and we have feedback. So how do we do this? We have lots of magnetic sensors dotted around the machine, and we measure the magnetic field. We know the magnetic field from the coils because, you know, we drive the current in, we design that field. So when you take that field away from the measured field, what's left must be due to the plasma. From the field, we infer the plasma current and its position both radially and vertically. And that's compared in a feedback to the desired position, and then the coil fields are changed. And we do that on about 100 microsecond time loop is our control system time. And that's dominated by the coils. It's hard to drive current into a coil quickly because you've got an inductive term, as you really need a lot of voltage to do that. So if our sensors show us that the plasma is moving out slowly, we'll increase the field in these 2 coils and try and push it back in. If we decide in our algorithm that it's too close to the center column, we'll lower the field in these 2 coils, and it'll sort of naturally drift out a bit because sort of current loops want to expand. So this works very well in research machines, and it's one of the really challenging areas to scale up into the commercial world. The reasons for this are the radiation environment gets a lot harsher. So we use a DD fuel. So we talked a little bit about merging hydrogen isotopes, and of course all reactions aren't created equal. So the deuterium and tritium is the easiest one to do on Earth. It happens at the lowest temperatures. We use deuterium and deuterium, one because tritium is majorly expensive, and you don't need it to demonstrate the plasma physics relationships. And secondly, if we go to tritium, I then have to write safety cases and spend a lot of my life talking to regulators about how we manage waste and things like that. So research machines tend to not use the real isotopes, the isotopes that are easiest to get to fuse. And when JET did, they demonstrated that it is directly applicable to change them over, looking at various sort of parameters. So when you go to this harder radiation environment, your sensors are going to take a battery, is kind of what I would like to say. And it's not just sort of radiation, you think about ionizing radiation, the UV radiation given off by the plasma is really quite immense, and it destroys a lot of the plastic insulation on wires and things like that. So it really needs a lot of thinking about. The other problem that isn't obvious is that it's easy to measure the change of a magnetic field. It's quite hard to measure a magnetic field. And so what we do is measure the change of magnetic field, integrate it over time, assume we started at 0 and we have the magnetic field. The longer you run a pulse for, the longer you've been integrated for, and the more your sensors will drift with that time. And so that gives you a problem to solve in how you manage the data, how you reset the integration at various times, and how you manage that drifted data. And that's being worked on by our diagnostic and plasma control group. And so those are 2 of the problems. There are a myriad of them, but we've only got sort of 45 minutes to talk about them. And I'm going to hand you back to Erica to wrap up.
Thank you, Rob. So we've talked through a lot in this talk, and I think we might have burned the number 100 million into your minds by this point. But if there's anything to take away from this, it's that why fusion is a really important part of achieving a zero carbon future. We really need to transform the way the world thinks about fusion from being something that's forever 50 years in the future to something that's actually on the cusp of being able to really transform our energy security. and help us provide energy for all. So that is the kind of main message that we're here to give you, really. So yeah, we were going to ask if you had any questions, but I have smelt the pizza in the room. So you're welcome to ask questions like this now, or if we just want to more informally come up to us, have a chat with us, that's also fine. So over to you guys. Hello?
I have loads of questions, to be honest. But I'll start with the last one, this one, the first one. I think what happened in August with the kind of first thing over 1Q was enough to power like 2-3 kettles or something. And obviously, as you said, kettles are like, they make it sound bad. I'm guilty, as you said, of kind of thinking of fusion's always 15 years away. What makes you guys think you can make it commercial by 2030?
So from my perspective, and I'll do it from like a very commercial aspect,
yeah.
I think fusion has really sat in a kind of quite a scientific research domain for quite a long time. And I think therefore it's not had the same investment and drive to kind of say we need to have aggressive timescales, we need to kind of really plan exactly how do we get to an optimal solution and how do we get to the best solution. So to me, I think we're so much more driven, and this is part of being privately funded, is that we have investors who want to see returns and they want to see milestones. And I think that really helps us to kind of push the development of technology. And if you think about kind of the timescales we've been doing stuff on, I mean, we were founded, it was 2013 we were founded. So what we have done in terms of technology development for spherical tokamaks and HTS in 10 years is astounding. And, as we grow and become bigger, I really do feel like if we can do that much in 10 years, we can do a lot in the next 10 years.
I think one way to look at it is there's problems that are solved and there's problems that are yet to solve. And we're slowly ticking them off. I'm not going to stand here and tell you there aren't problems to solve. There are many, numerous. We talked about 2 of them. Radiation damage. When you guys see us studying material science? Yeah. So radiation damage of materials is a huge subject. We can't recreate these environments on Earth at the moment. So how do you solve that problem? But if you look, we've been here before, if you look at the fission program after the war, and they weren't building the MAGNOX reactors in the UK, they had a similar thing. They couldn't recreate the conditions they wanted to rate their plant for. And so you can play tricks like do surveillance samples, things like that on that one example. So surveillance sample goes inside, its life a little bit ahead because it's in a slightly harsher environment than the component you want to survey. And so you test it periodically and get an answer that's slightly ahead of the plan. So things I think we've solved, I think we have a reasonable handle on the plasma physics. And one of the things it shows is performance. We talked about the Q of 1. Q gets related back to a triple product. So a lot of people will talk about Q equivalent. And the American funding agency, Department of Energy over there, is really keen on this Q equivalent, which is a measure of the number of particles of density you've got in your plasma. So you've got more there, you're just going to have more collisions, more reactions, more energy release. The temperature, so if you look at the cross-section data, and as I said, the cross-section is kind of a measure of how likely a reaction is to happen. It's broadly linear with temperature, and the temperatures we're likely to be able to achieve. So it can come in as a linear term. And then the confinement time, so how long can I hold that energy in the plasma? And that's related to, one, how much it radiates away, which is a cleanliness problem. So keeping it pure hydrogen helps that. Having sort of dirty elements like tungsten, like stainless steel, these kind of things in the plasma hurts that, and we're getting better at keeping them clean. The confinement time, so that triple product is a measure of performance. The last one scales with volume of machine. So I genuinely believe we could build you one now if money was no object. But I would be asking for trillions of pounds to do it. I would be building it on a major radius of something like 100 meters. It would be a monumental thing that you could probably see from space and would either be the greatest thing ever or a huge white elephant that everyone spoke about for a long time. So the game is really to try and condense it down, and you have to pick the point where it becomes feasible and it may be that the first ones aren't as commercially viable, because they're trying things out.
But this is part of the reason why we're still kind of like effectively prototyping. So the next device we're going to build, ST80HGS, I didn't choose that name. That's not aimed at being a fusion pilot plant. It's aimed at us saying, okay, let's push the technology we have that's ready into something and see how it integrates together. So I think, yeah, you can go ahead and try and build I think we're at a stage where people are saying, we can just go ahead and build a fusion pilot plant. But there's a fair number of people who are saying that who've never actually built anything. And there's a lot of skill in knowing how to put these things together and how things integrate with each other. And I think one thing I'd also kind of highlight from the technical side is HTS has been like a real kind of development for fusion, because it just makes the magnets and the magnetic fields you need so much more accessible, and it's game changing in terms of not having to have the cool down time that you need in copper magnets. So I think the fact that we're now, and like globally, it's becoming increasingly adopted, HTS for tokamaks accelerators, I think that has really pushed forward the timescales for doing it and have really brought it into kind of the closer future.
Yeah, I mean, it's definitely research, but I think we're closer than we've ever been.
Yeah, if you look in the future, so all the current renewable energy, and kind of the levelized cost of energy is expected to decrease. For wind, for example, by 2030 it's going to decrease by 40%. Now, I assume that fusion is very capital intensive. And so by the time it is, let's say, fully commercialized, you would have, let's say, the cost of generating this energy would be extremely high versus all the other ones, solar, wind, and other ones are cheap and, just way more affordable. So how do you see that side of the future for fusion?
So I think to me, there are two aspects to that. There's the first aspect that kind of all the advantages that fusion has over some of the renewables are still going to apply. Even if other renewable forms are kind of like cheaper per unit. I think also it's one of the things that we really are aware of and we think about as a company, that it's not just about, we want to get there first, we want to have the first commercial pilot plant, but we also want to have something that's not so expensive that it never gets built. So in everything we do, we are increasingly thinking about what is the end product and how do we make sure we have a competitive end product. Like, we can't, if we've got two materials to choose from and they have fairly similar characteristics, and maybe one is slightly better, but it's, thousands of times more expensive, that's not the right choice for us to make, right? So that's why we kind of think we have an advantage in the sense that we're having these kind of commercial thoughts now, and we're thinking with, how do we compete with these renewables? So I don't have a straight up answer. This is definitely how we do it, but it's a conversation that we're having all the time. Is how do we produce a solution, but a low cost solution?
I think so. We're targeting about £50 a megawatt hour, which is going to be more than sort of wind and things like that. I think one of the things I would say is the spherical tokamak is a lot smaller, so it's much less capital intensive. One of the things that's surprising when you build one of these plants, the tokamak itself will cost you about a third of the total capital cost. So the smaller you can make it, the capital cost comes down and the cost of electricity with it. What I would say is I'm not sure the levelized cost of electricity is measuring exactly what we want it to. As Erica said, fusion brings certain benefits like dispatchable power. So there are days where wind doesn't blow and solar's not available. So if we look back about 3 months, I think early December, we had an anticyclone over the UK, it was winter, there wasn't a lot of energy. And normally where energy sells for like 20 quid, 30 quid a megawatt hour, it was selling for £2,000, £3,000 a megawatt hour at the peak times. And so a lot of these things are about an energy mix. And you need dispatchable power, and the things that can do that for you are hydrocarbons, which have problems with climate change, and depending on what people do with carbon levies, the cost will go quite large. Fission plants, which again have their own challenges of capital cost. And so I think the Hinkley Point strike price is somewhere around £90 a megawatt hour, something like that. And sort of wind and that which is not as dispatchable. That's kind of the market. So I don't see us in direct competition with wind and solar. I see the competition with energy storage and the cost of the round trip of generating on a windy day, storing for the not so windy day, and then sort of really, when you take all those inefficiencies, the cost of that energy is our.
Yeah. And also we have like bigger costs for things now, and this is also a kind of a supply chain issue. So HTS is a really good example of this. That effectively, even like 5 years ago, like there was hardly anyone making HTS tape. And like even in the past 5 years, the number of increase in suppliers that we've seen is huge. Now HTS tape is still quite expensive, but as more and more people are using it, there's going to be increased demand, there's going to be more suppliers, that's going to drive down the cost. And essentially that's probably what's going to happen across the board with fusion, that kind of all of these technologies are going to get generated. There's going to be limited suppliers kind of like that exist now, maybe no suppliers that exist now, but these supply chains will build up, and there will be competition for the best resources, and that will increase overall, help to drive down costs.
And again, the smaller it is, the more modular you can make it, and the more off you produce of anything, the cheaper the unit cost is going to be.
On that point, so when I hear making a small modular machine, I also hear high energy density. That just makes it more and more of a material science problem. So in terms of halfway points, like are there other ways to commercialize the material science advances made while on the way
to we actually have an aspect of our business which is alternative technology applications. So it's one of the things that we actively look into and we think about is how can we apply all of the technology we're developing into different fields. So that's something that we definitely keep in mind, and it's so many conversations I've had with, for example, our supply chain manager, which is kind of about him saying, actually, this is great because if we could get some of this technology used in other fields and it was an earlier market entry point, we would drive up the amount of production of these things, we'd steady up the supply chains, and that would help us bring the cost down in future. So yes, that's something that we do very actively think about and see the benefits financially of doing something like that, but also just commercially to fusion business, it's really useful.
So, this is a question about money, because quite often investors want to see returns in 5 years. You've existed since 2013, and I don't think you've produced. I don't think you've made any revenue for yourself yet. Yes, you still have quite lots of interest from investors. You still have quite a lot of money spent if you have so many people in your employ, and you expect to have enough money invested into 2030. So I'm very curious to know how did you achieve private investment over so many years such far-flung prospects?
I think that the company started small. Is one thing to say. So the 3 guys who spun out of Cullen, and then when you cover in 5 salaries, it's not the same as covering 200 salaries. So really, it's been an exponential growth. And the key thing is we get given sort of milestones, and the idea is that these guys, we don't produce revenue for them, we don't pay dividends, but they make money on paper because the value of shares that's owned kind of expands. So last year we got the 100 million degrees, and in theory the share price went up. So we're going to go out, as Erica said, to build our next machine, and this is a very, very expensive machine to build. So we need to raise capital. So what we're going to do is sell a load of shares. We're going to cut everyone's investors. So let's say we're going to cut everyone's proportion. So we need to grow the nominal value of the business so they don't lose out. And we've got a myriad of investors. So, I mean, it's no secret, right? You can look it up on Company's House. One of our big investors is a guy called Simon Woolston. He's the owner of Next, the clothing store, and he was an early investor. So please remember, these guys, when they invest in things like that, they get a big tax credit against it. So they pay about 50% of the nominal money that they put in. And it's a gamble for them. It gives them something interesting to talk about. They've got a diverse portfolio of things they're investing in, things that are less risky and clearer, and things that, if it pays off, is going to pay big. It's like me buying a Euromillions ticket. If I lose my £2, I'm not ecstatic about it, but it's kind of like this. But if I win big. And so he's got investments like that, and he's got investments in, well, obviously Next.
So I'd say there's kind of another icier side of it. Is no one is investing in Fusion for short-term gains. They're just not. And if you were investing in Fusion for short-term gains, then I have a question about how you've ended up with quite so much money in the first place. So I think there is a kind of often a mindset in the people who invest in our company that either, they want to have a part of the next big thing. They want to have their name on it. They want it to go down that they were one of the people who backed Fusion. In its early days, they made it work. And I think there is just also people who are just generally in it for the longer run. They do see this it's a risk versus reward, and they're like, if this works, or as we like to talk about it, when this works, it's going to be a massive reward for them in terms of how big the markets are. The predicted markets for Fusion are absolutely ginormous. So even having a portion of that, let alone maybe a majority share, would be a very, very, very tiny return. But you're all right. We're not attracting people who are looking for short-term gain. That's not the aim of the game, essentially.
So it's people who could afford. It's part of a larger portfolio that's quite high risk, high reward. It's people. It gives them something to talk about. It's interesting. It's exciting. It gives them something to talk about. I think that's why they do it. I think some of them are altruistic. Bill Gates invested in one of our competitors in the States, Commonwealth. Jeff Bezos has invested in General Fusion, which is a Canadian company going to build something in Cullen. And so there's a lot of big names investing, and maybe they know something I don't, right?
Any more questions? We have to do some more informed questions as well.
I just found a note, in terms of applications of Fusion, is it just going to be for credit? Is there any other forms of generating revenue than just selling to something?
Oh, I presented on this a while ago, now I should remember. What did we say?
When we started as a company, we weren't going to generate power. And a lot of our early investors said, well, electricity markets we want to be in. So the idea was as a neutron source. So we use neutrons for various things. So you can burn up radioactive waste with it, create medical isotopes. So there are certain medical procedures that rely on like a molybdenum isotope that has about a 2-week half-life. And there's only about half a dozen reactors in the world, fission reactors today, that make them. And the original conceived idea was as a neutron source for this. And so you can sell heat, you can sell power, you can sell neutrons. The market for neutrons is a lot smaller.
Yeah. So heat is a good one, actually. Industrial heat, that's a biggie. Also stuff like desalinization, that's another market. But essentially, it could be that it's energy production to the grid, but it's also not impossible that if you had a big industrial complex where they needed heat or a desalinization plant, that they might have a dedicated tokamak providing power for that. So, a wide range of possibilities. And as we neutron source, but kind of as we touched on a bit more before, there's going to be lots of great technology developments that we have already made and we're going to make, which could have varying applications in other fields. So that's also kind of quite an exciting aspect.
Last one, you mentioned you want to reach to Q20 at some point, and this is going to lead to commercialization. When do you anticipate this to happen, considering technology?
So we are aiming for commercial pilot plant in 2030. That's the aim. So that's when we think we will be generating commercial revenue from Fusion.
And I think it's worth saying it's not just us, you know, the Chinese are backing this force really, really quite strongly. The state over there have 3 or 4 different programs that they're pushing. One with an ITER style reactor, one with a spherical tokamak, one with a accelerator. They're backing a lot of forces. The American government's getting very, very interested in starting to put lots of grants out in this area. So I think I saw a paper once. There was a couple of guys who worked in this a long time, and they looked at the kind of the funding model. And there's a baseline funding where you kind of pay to stand still because you know you're paying my salary to write risk assessments, keep everyone safe while we don't do a lot of physics. And there's kind of a sweet spot in the funding, and it's very non-linear. So the other thing to mention about the performance of these machines as well is it's very non-linear. The fusion curve, you don't have to go 20 times the performance parameter to get 20 times the Q. It's a very, very non-linear relationship in our favour, as far as I know.
Thank you so much.